In physical cosmology, cosmological inflation, or simply inflation, refers to the theory of exponential space expansion in the early universe. Today, the evidence for the Big Bang model is so compelling that almost no scientist disputes that it accurately describes the history of the observable universe. The common misconception about the creation of the universe is that in the beginning, the universe was tightly packed into an infinitely dense point. It then exploded into the present universe. Astrophysicists will tell you that this image of the Big Bang is inaccurate, despite the fact that it is commonly held. Welcome back to my channel. How cosmic inflation explains the universe as it is. First, there was no explosion comparable to that of an explosive detonation, in which fragments fly in all directions. There was no flying substance comparable to stars, galaxies, or even atoms. As the universe expanded and grew colder, atoms did not coalesce until approximately 380,000 years later, when temperatures cooled and it took even longer for larger structures to form. The Big Bang did not occur when the universe possessed zero dimensions or infinite density. It is merely a moment in time when the universe was extremely hot and dense, and the Big Bang did not occur at a specific location in space, but simultaneously throughout the whole space. And contrary to popular belief, the Big Bang model is not an explanation for the origin of the universe. Current scientific knowledge does not explain how or why the universe came to exist, or what caused its expansion. The Big Bang model describes events that occurred in the early universe, which led to the universe we observe today. This history is well understood, and has been verified by evidence that we can still observe 13.8 billion years after the Big Bang. Inflation reveals that the period of time before the Big Bang was extremely cold, nearly absolute zero, and devoid of all matter other than empty space, and that empty space carried the energy that expanded the universe to its current enormous size, and into its initial state before the Big Bang. In accordance with the inflation theory, the early universe expanded exponentially quickly for a fraction of a second following the Big Bang. In the early 1980s, cosmologists introduced this concept to address a number of significant cosmological issues. The horizon problem is one of these issues, along with others, like why is it so homogeneous, why its geometry appears flat, and where are the magnetic monopoles. In the earliest iterations of inflation theory, the universe expanded exponentially faster than the speed of light, according to the simplest version of inflation theory. It is believed that the inflationary epoch lasted from 10 to the power of minus 36 seconds, to between 10 to the power of minus 33 and 10 to the power of minus 32 seconds after the Big Bang. During this time, it expanded with a factor of at least 10 to the power of 78, going from being very small, to being very big, exponentially big. So the universe expanded faster than the speed of light, but you may argue that nothing could travel faster than the speed of light. Einstein's theory of special relativity demonstrates that this speed limit applies only to objects moving within space, and this restriction does not apply to space itself. I am certain that you have heard that the universe began smaller than an atom and grew to the size of a grapefruit. Keep in mind that these analogies can be deceptive because they suggest the universe has a boundary. It doesn't, there's only the universe and nothing else, there is no outside, and we have already discussed why the universe has no center, or at least have no center in the 3D world. It can have a center in the fourth dimension, which is the time dimension. At t equals 0, the moment the universe started, not in space but in time. A very good analogy is like an ant on a surface of a sphere or on the surface of the Earth. The ant can walk forever without finding an edge, but the interior of the sphere, of the Earth, if the ant can leave the surface and access the 3D world, the interior of the sphere, will find the center of it. The universe's center lies outside the 3D spatial dimensions, is in the fourth dimension. We need to see the inflation as a sudden burst. The universe continued to expand after the inflationary period, but at a reduced rate, in fact is still expanding even today. The inflation theory proved to be successful, but the particle physics mechanism responsible for inflation is unknown. It is like we know gravity, but a quantum theory of it was always out of our grasp. The fundamental inflationary paradigm is accepted by the majority of physicists, as a number of inflation model predictions have been confirmed by observation, but there is a significant minority of scientists that disagree. Common misunderstandings about the beginning of the universe, the idea that the universe started from a singularity that is a point of infinite density and heat is not correct. It is undefined and represents the extent of our understanding. According to the Big Bang theory, a singularity likely does not exist as a physical entity. It is a component of the standard cosmological model. According to the theory, the universe today is significantly larger than it was a billion years ago and than it was yesterday. Therefore, as one extrapolates backwards, the universe becomes smaller, denser, and hotter. As one continues to travel further back, one reaches a very small volume of space that is extremely dense and extremely hot. At some point in this extrapolation, our equations cease to function as the volume becomes zero. At this time there were likely other physical laws in effect, such as quantum gravity. There is no such theory yet, although steps towards a quantum description of gravity has been made by Maldacena, Susskind, Thuft, Verlind, and others. The universe is currently expanding, but galaxies are not moving apart from each other at the same rate. Only the intergalactic space is expanding, and only at a very large scale. Gravity plays a role as well. Gravity still holds stars together on smaller scales within a galaxy. While the universe may have originated from a small volume of space, cosmic inflation would have caused all points within that volume of space to expand. This expansion or inflation occurred everywhere in space. There is no center or location of the universe. Every point moved away from every other point. Expansion at a rate faster than the speed of light during inflation also implies that these points, which may have been initially causally connected, moved apart and became causally disconnected after inflation. Due to the fact that causality is limited to the speed of light, information cannot travel faster. As a result, there are portions of the universe that we will never be able to observe or detect, as no light or gravity from these regions will ever reach us. When we look out into space, we observe that the universe is uniform on large scales. The universe is extremely homogeneous and isotropic, which means it have a similar appearance in all directions. This can also be observed in the cosmic microwave background, or CMB, where the minute differences visible in the image correspond to temperature fluctuations of no more than 0.0001 Kelvin. To illustrate how inflation explains why the early universe was so uniform, let's imagine that the universe was completely random prior to inflation. Perhaps in one location the population density was greater than in another. It is comparable to the surface of a deflated balloon. There may be minute flaws, such as varying thicknesses and wrinkles, randomly dispersed on it. Imagine that this balloon suddenly expands to an enormous size in a fraction of a second. Later, the wrinkle on the surface of the balloon disappears. Any differences in the skin's density are diminished. This is comparable to what occurred during inflation, when a minute volume grew by a factor at least 10 to the power of 78. To address the flatness issue, imagine living on the surface of a very small balloon like an ant. The world would be two-dimensional. Nevertheless, if the balloon were sufficiently small, it would be evident that the surface was curved and that you were living in a closed or curved universe. However, if that ball were expanded to the side of the Earth, it would appear flat to you, despite remaining a sphere on a much larger scale. Now scale up to human size, and since the ball was much larger than even the observable universe, it would appear to be flat as far as the eye could see. Inflation stretches any initial curvature of the three-dimensional universe to a nearly flat state, despite the fact that it may have been notably curved to begin with. We do not know if the universe is flat or curved, but if there is a curvature, the universe is so vast, that the curvature has become so small, that it cannot be measured with the technology we currently possess. A closed curvature for the universe would imply that two parallel lines would eventually converge in our 3D universe, just as parallel lines on a two-dimensional balloon surface converge. How does inflation solve the problem of magnetic monopoles? The absence of magnetic monopoles observed in the universe. Theoretically, monopoles can only form at extremely high temperatures. These temperatures existed only during the Big Bang, but once they formed, they should have been stable enough to endure. The idea is that inflation would have rapidly cooled down the universe due to its rapid expansion, and that only monopoles created before inflation would have survived. During inflation, however, monopoly density would decrease exponentially. As a result, their abundance would drop to undetectable levels as a result of their low population densities. Looking at the CMB, the universe is not completely smooth. We can see that there are minute flaws and temperature variations. This is known as the anisotropy of the microwave background of the universe. You could argue that this undermines the concept of inflation. But no, because these small anisotropies are exactly what we would expect if the universe is not completely uniform. Inflation makes large scales, such as the CMB, appear uniform. However, the small anisotropy can explain the origin of the universe's observed structure. Prior to inflation, the universe was microscopic. During inflation, quantum fluctuations within the density of matter may have expanded to astronomical scales. And this is what we observe throughout the universe as the regions of higher density condense into galaxies, stars, and galaxy clusters. What can inflation tell us about the forces that hold together our universe? If only the visible matter existed in galaxies, there would not be enough gravity to hold galaxies together. With their current rate of rotation, they would simply disintegrate, or they would never have formed. Even at these high velocities, it is assumed that there must be other matter present, to produce a stronger gravitational field to hold the matter in place. That's dark matter. The physicists are calculating the production of primordial black holes, in a form of inflation known as hybrid inflation. An important requirement is that inflation must persist long enough to generate the observable universe from a single, small Hubble volume. This is required for the universe to appear flat, homogeneous, and isotropic at the greatest scales observable. The Inflaton field is the scalar field that drove the inflation. When reaches its lowest potential, inflation ends and it decays into other fields and particles. After this event, the universe continues to expand, but in the slower way that the original Big Bang model described. The scalar field causes the almost instantaneous exponential expansion that we call cosmic inflation. Unfortunately, we did not detect any Inflaton field, but the confirmation of another scalar field, the Higgs field, give the scientists hope in searching for the Inflaton field. So inflation theory solves several problems and raises others. We believe we are on the right track. I shall keep you posted with any developments regarding this matter. Thank you for watching.